Okay, so welcome back to the problem solving session for the Introduction to Fluid Mechanics course. And in this week, we will be primarily looking into the forces on plane surfaces, like how to derive the expression for force on a plane surface, and primarily looking into the significance of this center of pressure, these things. And first of all, I would just like to know if I'm audible.
Yes, sir.
Yes. Thank you. Thank you so much. Okay then. Okay. Oh, okay then. So I think we can start. Enough people students have joined already, so I think we can start. Okay. Thanks, Devanshu. Okay. So as per our regular agenda, we will just briefly go through the topics discussed by Professor Chakraborty. I'll just briefly go through the expressions that he derived and just briefly go through the concepts that he discussed, and then I will look into some questions that will be quite relevant and helpful for you to solve this week's assignment questions. Okay, and moreover, since this week's assignment questions seem like are quite involved, so it will take a bit more time for you to look into it. So that's why I would like to focus more on the assignment questions. More on the problems that we are going to do this week. So I'll give more time on that. So maybe the theory part may not be that extensive, but still I would like to give a nice balance. Okay then, so let's start our discussions. So Professor Chakraborty discussed about forces on plane surfaces. Again, he did a detailed derivation by considering a generic surface submerged in a plane and then finding the force that acts on it. Okay, and in order to understand the force that acts on it, he derived a certain parameter or quantity which is known as the center of pressure. Okay, so let me just maybe hide the notes here. So could any one of you please tell me about what do you mean by center of pressure? It seems that the mic part is alright, so you can either speak up or just write in the chat box. So both of them are fine. So can anyone just discuss about what the center of pressure means, what you understood by center of pressure, and what is its significance? I'll wait for some time, then I can continue. It's fine. Okay, no issues. It's fine. So the center of pressure. Okay, so I will discuss it, but if you have any doubt, you can still ask. But I will just give a definition about it, and hopefully, when we look into some examples, you will understand it better. Okay. So the point at which pressure acts. Yeah, exactly. So pressure, like see, when you study mechanics, there is a concept of center of gravity. Like we center of gravity is a point in a body where we assume that all the force or the mass of the body acts through that particular point. So whenever we are balancing that body with respect to its center of gravity, you will see that the body is perfectly balanced since all its weight or the force that the body entails is acting through that particular point. So similarly, when a body is submerged in a fluid, of course its mass is quite relevant there as well. So the mass of the body will act through its center of gravity. That's fine. But since now we know that once the body is submerged in a fluid, there is another type of force that acts on the body, that is the buoyancy force, right? So this buoyancy force, as Divyanshu mentioned, it imparts some pressure on the surface area of the body, where this pressure force, because of the fluid that on which the body is in which the fluid in which the body is submerged, this pressure force acts through the center of pressure, or known as Yp, or any kind of notation that you mention. So here at this point in this expression, it is defined as Yp, and it is given as Yc plus Ic by Ayc. Okay, so this derivation I'm not going to do again. There was a detailed derivation taken by Professor Chakraborty, so you can just go back to the lecture and find it out. In fact, you can try it out yourself as well. So here you can see that there is one thing to know, is that this Yp is, as you can see, is always greater than Yc. So it means that if a body is submerged in a fluid, its center of pressure will always be at a greater depth compared to its center of gravity. Okay, for example, if, let me take a case, like say this is a flat plate. Okay, so for example, this would be the 3D shape, and this is submerged in a fluid. Okay, so this is, let me consider this as a free surface. Okay, so the center of gravity, or the geometric center of this body, would be through its central axis, right? Okay, through its central axis. Let's say this is at a depth of, I'm sorry, anybody? At a depth of, say, h bar. Okay, so what this expression tells us, that this center of pressure would be at a greater depth compared to its geometric center, or the center of gravity. Okay, so it will be at a depth, say, hp. Any notation you can use, you just have to mention it in your answer, so it's fine. At a greater depth, because along with this center of gravity, yc, there is an additional term that is added in this term, in which all the parameters are positive. So Yp will be greater than Yc. Okay, so properly define it. The point P is not a center of pressure, and it is the point through which the resultant pressure force, or force due to the pressure, passes. Okay, so the main reason behind this discrepancy between the center of pressure and the center of gravity is because of the pressure distribution. So in the last discussion, or in the last week's discussion, we ended with the hydrostatic law that stated that dou P by dou Z, I should write dP by dZ is equal to minus rho g. So here you can see that, or you can write something like P of Z is minus rho gz. Okay, so here you can see that this pressure force, or is a function of z, which increases, or basically the magnitude of this pressure force, if you consider the magnitude, increases with the depth. So it's a function of the depth in which the body is being placed. So intuitively also you can consider a scenario where, for example in the case of car accidents, right? So whenever the car is, like, if it goes inside a river or a lake, if the car submerges very deep below this lake or river, you can see the passengers inside the car find it very difficult to open the car doors, right? It's primarily because of the high pressure that they experience when the car is being submerged in that point. So it's a very vague example, but these are the scenarios that you can understand, since as we go deeper and deeper, the pressure because of the fluid increases, right? So it increases linearly with the depth. So that's why this diagram shows a very nice schematic distribution of this pressure. So you can see that this is not the actual distribution of pressure. It's not uniform, and it's actually something that increases linearly with depth. Okay, and again there is one question in the this week's problem solving part that will be quite relevant to this diagram, so we'll look into it once when we get there. But this is the reason why the center of pressure and the center of gravity is different in the case of submerged bodies. I hope it is clear till now. So any comments? Okay, so let's take one example. So it's the similar example that I discussed here. So we're just putting more terminologies now. So consider that we have placed a particular rectangular plate at a certain depth, say where the upper edge of the plate is a depth of A from the free surface, and the height of this plate is say h, then the force, the net force that acts on this plate would be given by rho g into A into hc, where hc is the center of gravity of the body. And see, this force, the pressure force, is not determined by the center of it's not, see here in this you can see it's not a center of pressure that comes in picture, but rather the center of gravity. Okay, because because center of pressure or yp is the point at which this force acts. So the magnitude of this force is governed by the center of gravity, but the point of application of this force is given by the center of pressure, it is yp. So these are not to be confused with. So this is something that you need to understand. Okay, and not to be confused with. So if we take more examples, you'll understand it more properly, but this is just some subtle detail that I wanted to mention. Okay, so so in this case, again this example was taken by Prof. Chakraborty, so if I am not able to clarify it further, you can just go back to the lecture, but something just to revise. Then this pressure force then can again be simplified further. So rho g is same, then A is will be given by the area of this plate, that is B into H, and HC would be the center, the location of the center of gravity of the body. Okay, so here center of gravity would be for this plate would be h by 2 with respect to the plate's height, let's say. So it will be h by 2, but we also have to consider depth at which this center of gravity is located. So it will be given by h by 2 plus this depth A. Okay, so that's why it is A plus h by 2. Then the center of pressure, or the point at which this force acts. So now you will see, when we take some more examples, we will see why we need to find the this point of application. So you will see that we will be dealing with finding the moments of these forces. So to do that, you will need to find the point of application of these forces, right? That's why the center of pressure becomes quite relevant. Then the center of pressure for this particular case will be given by, again, the general formula, that is yp is equal to yc plus ic by ayc. Then yc, the location of the center of gravity, is given by A plus h by 2 plus the area moment of inertia of this particular plate, that will be b h cube by 12. Since we are considering the area moment of inertia with respect to this horizontal axis, that it is then b h cube. Okay, if we are considering the vertical axis, then it would have been h b cube by 12. Okay, then area is again bh, and yc, or the center of gravity, is at the location of A plus b by 2. Okay, so this is a generic expression. Again, once we put in some values, you will get an idea. Let me see. Okay, so this again Prof. Chakraborty mentions about presenting this hydrostatic stresses in the Mohr circle. So Mohr circle is again a topic of discussion that is beyond the scope of this course, but again it's again quite relevant, since if you had taken some solid mechanics course, or say for example strength of materials course, you will be quite aware with the concept of Mohr circle, where it is used to quantify the shear stresses and normal stresses that act on a particular body. So similarly, since in this case the only stress that acts is the compressive stress because of pressure, so the Mohr circle is just circled down into a particular point where it is, since a compressive stress, so it will be negative, so it is given minus p 0. Since 0 implying that there is no shear stress that acts in this particular case. Okay, again it's not something that we will deal with in your assignments or exams, but something that will help you to correlate these two concepts. Again, since maybe it may seem different, since fluid and solids are can be considered as two separate branches of study, but still, since it's a mathematical deductions of the analysis is the same in the case of solids and for the stress analysis in solids and fluids, that's why the Mohr circle becomes quite relevant in both the cases. Okay, so let us look into another example. Here we'll be dealing with here it will become quite more relevant why we are considering the uh, center of pressure and why it becomes important in this kind of analysis. Okay, so so again, all these examples that I will deal is already dealt by Professor Chakraborty. So I'm just revising it just to make sure you have no doubt in these examples. Okay, then again, in this example, here we consider a gate that is being hinged at the bottom of the surface, which is shown here. It's hinged here, and this gate is able to move in both the directions. Okay, let's say okay, or let's say it's just able to move in this particular direction, open in this particular direction. Okay, and the mobility of this gate is governed by this hinge. Then because of the fluid pressure, where the free surface is denoted here, and because of this fluid pressure, this gate will tend to open, as you know, since there will be hydrostatic pressure forces that will act on this gate, so the gate will try to open up. And since we want to control the motion of this fluid, like we want that it should not open by itself, rather it should open at the point where we want it to open. For example, in the case of dams, like the gates in the dams, like we do not want it to open automatically. So whenever we need the water in the downstream area, we will open the gate. So we want to have control over this motion of this fluid. That's why in this question it's specifically asking, like, if the shape of this gate is in this semicircular shape. Of course, in the case of dams it's not such kind, but just to put in more concepts altogether, like when if you're dealing with a bit more difficult geometry, then again you need to revise your geometry concepts. Then again, it's a good exercise for you. That's why this kind of geometries are kept. But in practical scenarios, in dams, usually we do not deal with such kind of geometries. Okay, it will usually be a simple simple square or rectangular shaped gate. Okay, but still, since in this question this is the shape that is being given, we have to deal with it. So the shape of this gate is of semicircular shape, where the base of this gate is attached below, and this is the place where it is attached with the hinge, and we have to apply a force F that will keep this gate closed. Okay, so I hope the question is clear. So again, to reiterate, the fluid is being contained in this, but is held together by this particular geometry or design, and the lower portion of this design is, or of the structure, is able to operate with respect to the hinge. And since it holds a fluid up to a certain depth of h, this fluid will impart pressure forces on this particular gate, which will try to open this gate. But since we want to have control, we are applying a certain force up to a point where we have to prevent this gate from opening, and once we want to open this gate, we can remove this force. So the question is, what will be the magnitude of this particular force F? Okay, and since there are no numerical values given, so we have to find an expression for this particular value of F. So I hope the question is clear. So let us look into the solution methodology. Okay, so let us consider let me zoom out a bit. Okay, let us consider the free body diagram of this particular gate, since this is the region of interest in this particular problem. So let us find the free body diagram of this particular gate. Okay, so the mass of the gate again will act in the negative z direction, and it will be balanced by the reaction forces in the y direction at the point O. Okay, then the force F acts on the upper edge of this gate as shown in this diagram. So it is shown here in this direction, and the pressure forces, because of the water contained in this structure, acts on the gate in the positive x direction through the center of pressure. So now the concept of center of pressure has found its relevance. Okay, and this center of pressure, location of center of pressure is at a distance of y1 from the bottom surface. Okay, so this is y1. Let me just draw it so that will become a bit more clear. So this is y1. Okay, so if we do if we find the summation of all the moment with respect to O, then we will find that this F times R, that is the length, the length of the gate is R. So F times R would be balanced by Fp times Y1. Okay, and Y1 would be given by H minus Yp, since if we consider the depth of the central pressure from the free surface as Yp, then Y1 would be this length minus this length. Okay, so it is H minus Yp, and then again Yp can be found out by Yc plus Ic by Ayc. So the task is to find the expression for F. So again, from initial thoughts, it might seem them that it's quite simple. Like we can just write F as Fp times Y1 by R. But again, the difficulty arises in the case where we do not know the expression for Fp. So this simple analysis becomes redundant in this case. So we have to take the help of some another methods. So Professor Chakraborty mentions the another method to be integration, that we want to find the net force that acts on this gate through integration. Okay, so let me just again, he discussed this integration very thoroughly, quite extensively in the lectures, but let me just go through it briefly. So if you have any doubt in the process, you can ask. I'll try to clear it out as much as possible. Then let's see, then we can continue. Okay, so I think you understood the requirement of integration in this particular case, because since we do not have the expression for Fp, and we need to find F in terms of the parameters that are given in the question, and Fp is not that given parameter. Say the given parameters will be R and H. Okay, we need to find the expression for force in terms of R and H. So, and since we do not know the expression for Fp, we need to take the help of integration to find the expression for F. Okay, so let us first look into this diagram, where we consider the elemental area and the particular heights and depths. Okay, so first things first, the center of gravity. Let us find the center of gravity of this particular semicircular gate. Okay, so in diagram it may seem like more like an ellipse. I'm sorry for that, but it's actually a semicircle. Okay, sorry for the discrepancy in the diagram and the explanation. So it's actually a semicircle. So let me just denote it as semicircle, so that once if someone checks the notes, they are not confused. Okay, so I think it is more clear now. So the center of gravity of a semicircular plane is at a distance of 4r by 3 pi from its base. Okay, again, it's a geometrical concept, and you will see that there will quite a few times when you have to go back to your basic geometry understandings and need to understand how we can find the center of gravity of some particular shapes. Okay, again, it's a good exercise, as I already mentioned. It helps us to revise those concepts again and again. So it's a good exercise. So you can just look into the internet, or if you remember, that's fine, but otherwise you can look into the internet and find the center of gravity of the particular shapes. So in this case, for a semicircle, the center of gravity is at a distance of 4r by 3 pi from its base. Okay, so okay. So the location of center of gravity, that is Yc. I think I didn't denote it here. So let me denote it as, say, if I extend this line. Okay, then from the free surface, the location of the center of gravity would be at a distance of, this is Yc, right? Yc. Then Yc would be at a distance of h minus 4r by 3 pi. Okay, I hope this part is clear, how Yc is h minus 4r by 3 pi. Okay, So let us consider a particular elemental area of this form. Since we need to find the net force that uh, acts on this semicircular gate, it will basically be the integration of the pressure forces times the area. It will basically be integration of PdA. Then we need to find the elemental area to carry forward the integration and find the respective expression for pressure. So that's how we do. So we need to find the elemental area. So the elemental area here is considered to be of this form. Where the elemental area dA is given by r dr d theta. Okay. Where dr is the length. Basically, if you consider it as a something like length times breadth, so the arc length is r d theta and the width is dr, right? This length is dr, so the area would be r dr d theta. It's again an approximation, but it holds quite well. Okay. Then the depth of this particular elemental area, only this particular elemental area would be given by, if this is the distance of, say, this is a distance, this elemental area is a distance of r from the center of the semicircle, then this vertical height would be given by r sine theta, right? So again, this diagram becomes quite messy, but what can we do? Just it is what it is, right? We cannot change it. So this depth would be r sine theta, or height would be r sine theta. Okay. Then the depth of this particular elemental area would be at a distance of h minus r sine theta. So again, you may ask, like, why you are finding this? Because since we need to find the pressure for that particular elemental area, and pressure is a function of depth, so this particular elemental area is a depth of h minus r sine theta, and this depth would help us to determine the pressure that acts on this particular elemental area. Okay. So then I will just go beyond this diagram and I have to come back again and again to compare, so it's fine. Then similarly, then the force that acts on this particular elemental area dF would be given by P into dA, right? Pressure times the elemental area. It would be, pressure is given by rho gz, where rho g is constant and z, that is depth, is a distance of h minus r sine theta. Okay, I hope it's clear how we arrived into this part. And the elemental area is r dr d theta. Okay. So now if we take a moment with respect to O, okay, so dH would be dF times r sine theta. Okay, because you have to take the perpendicular distance from the hinge or the center, then, or pivot, anything you can say. So perpendicular distance would be r sine theta, right? So the moment would be dF into r sine theta, or the elemental moment dH would be this entire expression times r sine theta. Okay, so if you do that, you will get h. You have to consider this r as well. So this r will already have, if we do it, if we multiply this r here, it will become hr minus r square sine theta, then rho g dr d theta. Now again, you need to multiply one more r sine theta to take the moment, so it will become hr square sine theta minus r cube sine square theta rho g d theta. Okay, I hope it is clear till now. Thumbs up or yes, anything would be good. Okay, thanks Pradeep, thank you so much. So then the summation or total moment of this area with respect to O would be given by the double integration of this particular O. I am missing a dr here, I guess. I'm sorry for that. It would be one dr as well. So the double integration of this particular expression here. So it would be where r varies from 0 to capital R and theta varies from 0 to pi, because the angle, if we consider from here, then it will vary from 0 to pi or 180. Okay. then once you do the integration with respect to r, it's again, if you do respect to r, it's very simple. H is constant, so r square will become r cubed by 3. Then sin theta will remain constant. This will become r to the power 4 by 4. Then r to the 4 by 4 sin square theta. All this term remain constant. So something what we have already done here. Then we just replace sin square theta by 1 minus cos 2 theta, so that we can carry forward the integration with respect to theta. Then the integration is from 0 to pi of rho g, where the integrand is rho g hr cubed by 3 sin theta minus r to the 4 by 4 1 minus cos 2 theta by 2 sorry, d theta. Then once you do the integration with respect to theta, you will get rho g integration of sin theta would be minus cos theta, so hr cubed by into minus cos theta, where theta varies from 0 to pi, and integration of this would be 1 by 2 would be theta by 2, or you can just take 2 out here, so it will become theta minus integration of cos 2 theta will be sin 2 theta by 2, which is written here, and theta will vary from 0 to pi. So once you put the value of this theta in this expression, you will simplify it further, so you will get something like Fr, because the net moment, the summation of moment is balanced by this force, right? It's balanced by this force, right? So it will be Fr would be equal to rho g 2hr cubed by 3 minus pi r to the 4 by 8. Okay, then once you take r in here, so you get then final expression for f, which is rho g is equal to hr square by 3 minus pi r cubed by 8. Okay, I hope this is clear. Again, we will do a similar exercise in the questions, one of the questions that we discussed today. So it's fine. Once you try yourself, you will be much more clear, okay, regarding this. So now let us discuss the next topic, that is the force on curved surfaces. Again, this is a topic I think that is much better when you take some examples to consider, and there are 2 examples, I guess, I don't know, maybe 3 examples for this similar concept, which helps us to understand this topic even in a much better way. Okay, so but nevertheless, let us just once go through it, this particular case, very simplified case, where you consider a curved surface BC submerged in a body, submerged in a body of fluid, and we want to know what are the forces that acts on this particular curved surface. Okay, so a general practice is to decompose the force that acts on this curved surface in terms of its horizontal and vertical component, and then finding the net resultant force, which will basically be F is equal to Fh square plus Fr square. Quite simple. So that's why the general practice is to dissociate this force into these horizontal and vertical components. So to find horizontal forces, as Professor Chakraborty might have mentioned, the horizontal forces that acts on these surfaces would actually be the force that acts on the projection of these curved surfaces. So the projection of this curved surface here, BC, would be a rectangle of, say, it's a particular sector of a circle. Let us say, for example, the simplified case, say like this, and say the radius of this particular circle is r. Then the projected surface area of this particular curved surface would be r times L. Let L be the depth, or to just r times W, where W is the width or depth of this particular shape inside this particular diagram. Okay, the projected area, and the vertical force is basically the weight of the fluid that is being held by this particular surface. Okay, so that's the conclusion that we get here. So in both these expressions, so we will get more understanding when we take one example. Okay, so consider this example where where there is a cylindrical shape where the fluids are being contained in this particular shape. Okay, where this half of this particular cylinder holds fluid up to this region, in this region. Okay, and the other half of the cylinder, where the depth is again quite is less than the left hand side, holds the fluid in this particular region. Okay, so again, as I already mentioned, the general practice is to dissociate the force components into its horizontal and vertical components. I'm sorry, the force into its horizontal and vertical components. Okay, so the vertical force, as I mentioned, is the simpler one to find, because it's just the weight of the fluid that is being held within this particular curved surface. So it would be, in this case, it would be this volume of this weight because of the volume of this entire fluid. I'm sorry, just give me 1 second. The volume of the fluid that is contained in this container, it is of this shape, so we can simplify it by considering a half cylinder in this case and a quarter cylinder in this case, right? So that's what we have done here. So the volume of the fluid in this half would be pi r square L by 2, and in this would be pi r square by 4 into L. Okay, and the density into G, that will give the weight of the fluid, the weight of the total fluid that is being held by this particular curved surface. That is the vertical component of the force. Again, the horizontal component of the force is the force that acts, the pressure force that acts on the projected surface of projected area of this curved surface. So the projected area of this curved surface in this left hand side would be the rectangular part of say width or say length 2r and breadth of the depth of this length of this cylinder, that is L. Okay, so it would be 2r into L. So the pressure force would be, or FH1 in this case, FH1 would be rho F into G, this is rho times G into the area, it is 2r into L, that is the area, projected area of this curved surface, times the center of gravity of that particular surface, the projected surface, there would be R, right? Similarly, the second horizontal force that acts in this direction would be given by rho times G into the projected area, that is R times L, right, times the center of gravity, because the center of gravity of this would be a distance of R by 2, right? R by 2. Okay, so this is given here. So again, it was simple case. It was a simpler case. Let us consider a bit more involved example. Again, this example is a bit different because here again we cannot take the help of the general practice. So here what we do was, initially we did was to just find the, since all the parameters were given, we found out the expression for FB and FH. But since in this case, this particular example, it is a bit more complicated, so that's why we need to take some different methods to find the components of force. We cannot just directly take help of the geometrical parameters that are defined. Okay, so in this case, again, see if anybody just joined the meeting right now, let me just reiterate these examples that I'm discussing now. Again, we'll discuss Prof. Chakraborty, so you can go back to the lectures, but just so that I can help you to revise the concepts so that you can apply it thoroughly in the question answer part. I'm revising it. Okay, so in this expression, in this question, the curved surface is given by this particular black line, okay, which holds a fluid up to this particular height. Okay, it is at height of or depth of D, where free surface is denoted by this particular shape, and the width of this plate is W. Okay, so we need to find an expression for the net resultant force that acts on this particular surface, and there is no other parameter given, so we do not know the exact geometry. Is it a semicircle or ellipse, anything? So they have given a mathematical expression for this particular curve, which is given by x equal to ay cube. Okay, so it's a cubic curve with respect to y. So we know this for sure. So now again, since no other parameters are given, so again we need to take the help of integration. So it's just a regular, I must say, not regular, I would say a general procedure, like if the shape of the geometry is not generic, where you just can directly apply some formulas to find the area and then find the pressure and then just find the resultant pressure force. If that's not the case, like if you're not given these particular parameters, then you need to take the help of integration. So since in this case also we're not given such kind of things, we need to take the help of integration. So similar to the previous case, we need to find an elemental area, the depth of this particular elemental area, so that we can know the net pressure force that acts on this particular elemental area, then integrate it up to a depth, up to a height of uh, uh, up to the height of h, then find the net force that acts on this surface. Okay, so okay, I think I have to check once, but let us just continue for now. Just 1 second. Okay, you can just look into the diagram and try to understand different terminologies. I'll just have to clarify one thing. Okay, just give me 1 minute. I'll just have to clarify one thing. So okay, so yeah, so the integration, as I will just check the limits. So it seems I have done a mistake. I will just look into it once. I'm quite sure of it, but still I have to verify it once, and then I will discuss it properly. So let us look into the integration part. Okay, so let us consider this elemental area, like quite similar to what we have discussed in the example in the previous examples. So let us consider a particular elemental area of length dl. Okay, so this is the zoomed in version of this particular elemental area, which is at an angle of theta with respect to this vertical line, okay, of this particular axis. Then it is at an angle of theta from this particular vertical line. Then if we zoom in this particular elemental area, then you can dissociate this length into its horizontal and vertical parts. So dl, so we can see that dy would be dl sin theta and dx would be dl cos theta. Okay, and similarly the net dl can be given by square root of dx square plus dy square. Okay, quite simple. Just take the square of this, then sin square theta cos square theta will turn out to be 1, then you will get dl. Okay, so the net force that acts on this particular elemental area would be given by pressure P times dl into W. Okay, where pressure P would be given by rho g times d minus y. Let us look at how. So in this case, the depth of this particular elemental area would be at a distance of, say if the center of gravity of this particular elemental area is at y, okay, then it is the depth of this particular area would be a distance of d minus y, right? D minus this length will give you the depth of this particular area. So the pressure force that acts on this particular area would be rho g times d minus y into the area, that is dl into w. So the net horizontal force that acts on this particular curved surface will be given by dfh will be given by pw into dl, that is the net elemental force times sin theta. Okay, so let me just dissociate the forces as well. So if this is the force, then the horizontal force would be f sin theta, right? The net force times sin theta, and the vertical force would be f cos theta, right? So the horizontal component is given by pw dl into sin theta, where we know that dl sin theta is dy from this expression, then dfh is pw into dy. Pressure is again rho g d minus y, so dfh would be rho g d minus y w into dy. And the net horizontal force would be from integration from 0 to this part I am a bit confused. I think I made a mistake here. It should be from 0 to d. Okay, can you just clarify, is it d in the lecture notes? Otherwise I have to check in the it should be d because the depth of the fluid is up to d, but you can just clarify. Okay, I might have made mistake in my own notes, that's why I'm just trying to verify. It should be d, but if it's something else you can just let me know. Okay, so this is the horizontal force expression for horizontal force. Once you do the integration you can find the expression for Fh. Similarly, the vertical force component is Pw into dl cos theta from this part. This also angle is also theta, so Fv is F cos theta, so dFv would be Pw dl into cos theta. Okay, then again the depth pressure force is rho g d minus y w times dl cos this dx, so it is dx. So the interesting part now is that you can see that the initial variable that you have was y. Okay, you have y. So but the integration that you need to do is in terms of dx, and you now cannot I must say, you can, of course you can change it from to y as well, but you need to deal with some cube roots, then which may make the integration a bit more complicated. So to simplify it, instead of changing y in terms of x, you can just change dx in terms of dy. Okay, so if you have x as ay cube, let me just write it, x as ay cube, because we are doing integration over this particular shape, right, given by this diagram. So so we can just consider elemental length dx in terms of y, right? So now dx, if you take the derivative of both sides it would be 3a y square dy. Okay, then just substitute this value here, so we will get Fv is equal to y, again integration from y equal to 0 to y equal to d rho g d minus y w into 3a y square into dy. Okay, again the resultant force, once you carry forward the integration, then you can find the resultant force as F is equal to Fh square plus Fv square. Okay, so I hope it is clear till now. So let us look into the next part. Okay, so this part, the stability part, I will try to go a bit faster because it seems we are short in time, because there are three extensive questions in the today's discussion, so I will give you more time on that. So I'll try to cover up this part as soon as possible. Okay, but again if you have any doubt you can stop at me at that time and ask me. Okay, so in the next part Prof. Chakraborty discusses the stability of floating and submerged bodies. Okay, and again he takes quite extensive examples and gives us a very proper idea of why this is important in real life scenarios. So in the case of submerged bodies, so you can see that in the case of submerged bodies, or in the that can be said as bodies that are completely immersed in fluids. Okay, and this is this case is again valid for both water and air, because if we consider ourselves, say sitting right now, we can consider ourselves to be completely submerged in air, right? If air can be considered fluid, then we can consider we are completely submerged in air. So this stability criteria is quite relevant in the case of air and water as well, but since the buoyant force because of air would be quite irrelevant in application, so that's why this stability scenario does not become quite relevant in the case of air, but conceptually or theoretically this is relevant in both the cases. But so when we are discussing the stability of submerged body. So in a practical purpose, not a theoretical purpose, but in practical purpose, we are just considering bodies submerged in water. Okay, because water, it is the liquid that is being found most extensively in Earth, and all the say engineering scenarios where we have to deal with floating and submerging are related to water. So the fluid that is of primary concern is water. Okay, so let us consider this example, and this shape is again quite I must say quite efficient in describing our scenarios. Okay, so this large part denotes a higher surface area, so would take into account the higher buoyant force that would act in that particular direction. Okay, and the center of gravity, you can consider that a particular weight that is being attached to this bottom part. So the center of gravity is being you can say shifted in the or more affiliated toward the downward direction. Okay, or downward part of this particular shape. Okay, so that's why if the body is being placed in this form, in this particular form, then the center of gravity is naturally in lower compared to the center of pressure, or the center of buoyancy, I can say center of buoyancy. Okay, and the weight of the body will act to the center of gravity, and the buoyant force will act to the center of buoyancy. Okay, so in this case, if is in this configuration, then the buoyant force is being balanced by the weight of the body. So stability comes into the picture when we are giving a particular displacement to this body. Okay, and let me just introduce to you the concept of stability as well when we are dealing with it. So stability in this case seems like quite okay, I must say geometrically related. I can say like geometrically related. Like if a body is being displaced way beyond its threshold, then it gets displaced. Okay, it falls down, or is it like displaces a lot from its initial position. Or in this case, it will basically mean that if you're displacing the body to a certain angle or angular displacement, say theta, so if the body is unstable, then the theta will tend to increase, and basically the body will fall down, right? But in the case of fluid mechanics, stability is itself a very huge topic or topic of discussion. So right now we are not even dealing with flow, we are just dealing with fluid statics, but eventually we'll see that we will dealing with fluid flows. Again, we will classify it into laminar and turbulent, but there is an interesting region known as the transition region. Okay, so the concept of stability becomes quite relevant when we are dealing with this transition region flows. So it's a brief overview. Stability, the study of stability is again quite conceptually quite similar to what is discussed here. So for example, it is basically like if we are giving a slight perturbation or slight disturbance to particular fluid parameter, so what does, and then how does these parameters behave with time? Do they diverge out with time? Basically, do they attain very separate values as the time progresses, or they get this displacement gets diminished with time, and then it again gets back to a initial, or get back to a stable form, or attains a different stable form? So this is the basic analysis of or understanding of stability, just to give you a brief introduction. But I think it's quite difficult to digest now, but stability itself is a very extensive topic of discussion. But conceptually, the same principle is applied here as well. So in this case also, we are applying a certain displacement to this angular displacement to this particular body, say for angle d theta, and we are seeing whether the application of this small displacement d theta results in this body to fall down or get back to its initial configuration. Okay, so if it falls down, it will basically mean that the configuration is unstable, and if it get back to its initial configuration, it will mean that the body or the particular scenario is in stable condition or stable equilibrium, as mentioned by Professor Chakraborty. Okay, So let us consider this case where the center of buoyancy is above the center of gravity. Okay. So now if we give a particular displacement, angular displacement to this body, then the center of buoyancy will act along this direction and the center of gravity will act along this direction, in the downward direction. Okay, and these two forces, as you see, are acting in opposite direction and are being separated by a particular distance, say dr, for example. And since these two forces are acting in opposite direction and are separated by a particular distance dr, these two forces will constitute a couple. Okay, and you'll see that this couple or the moment is in the direction opposite to the direction of our displacement. So since to displace this body we have to apply a displacing moment, or let me just name it as displacing moment. I don't know what Prof. Chakraborty has named it, but displacing moment, for example, it's just a term that I devised right now for this example. Okay, so displacing moment is along this direction, that's why this body has tilted in this direction. But the restoring moment, because of the direction of the buoyant force and the gravity force is along this direction, so it will tend to restore the body to its initial configuration. So in this case it is at stable equilibrium. Okay, but again this does not mean that this theta is irrelevant to the direction of restoring moment. Okay, for example, if you supply this d theta to be very very large, like if you just displace it to say up to a certain distance even here, then again it's very difficult for the body to get back to its initial configuration. Okay, but so this stability criteria is only valid for small displacements. Okay. So here you can see that the stability criteria for submerged body is governed by the location of your center of buoyancy and the center of gravity. So if B is above G, we attain a stable equilibrium given by this example. Similarly, you will see that if you try to deduce a scenario, take into the case where G is above B and then try to find the direction of the restoring couple, you will find that it will constitute an unstable equilibrium. So you will see that if G is above B, say if G is above, G will act in this direction, B will act along this direction. So this moment will be in the direction of the displacing moment. So rather than restoring the configuration to its initial position, it will tend to displace the configuration even further, thus resulting in an unstable scenario or unstable equilibrium given by this. Okay, and if B is equal to G, then we say it is a neutral equilibrium. So if we give some displacement to the body tends to stay at that particular modified configuration, rather than it does not even displace further or get back to its initial configuration, it just remains like this. Okay, so I hope this part is clear. The stability of submerged bodies. Okay, so I think it's clear. So I just discussed a bit about the stability extensively in the previous part, that's so that I do not have to discuss thoroughly about stability in the part of floating bodies. Okay, so as you already saw that the stability of the submerged body were governed by the positions of the center of buoyancy and the center of gravity. But in the case of floating bodies, you will see that instead of center of buoyancy, there is another term or another parameter that governs the stability of the floating bodies. So floating bodies will basically mean that a part of the body is submerged in the fluid and it's basically partially immersed. Okay, and so we can consider that body to be floating on the surface of the fluid. But in actuality, some of the portion of the body is immersed in the fluid, which then again is the result, is the I must say reason behind the buoyancy force that acts on the body. Because if the body does not displace any fluid, then there is no buoyancy force, right? So the body has to displace some fluid, then the equivalent amount of force would a buoyant force that will act on the body. Okay, so let us consider this example. Again, I will not go to the derivation of the this derivation. So I'll just try to explain you the geometry and the concept, and then directly go to the expression or the metacenter or the metacentric height. So let us consider this particular scenario where a body of this particular shape is being submerged in, partially submerged in water. So basically it is floating. So it's just the side view. So it is basically of this shape, like again something like this in 3D. Okay, so again, to understand the stability criteria, we have to apply some particular displacement. I'm sorry. A particular displacement to this body. So we are applying a displacement in this direction. Okay, we are applying some particular force that displaces the body from its equilibrium position. Then we see that the center of gravity, that is G, will remain constant and act through and the weight of the body will act through this particular point only, that is the center of gravity. But the interesting thing is now that since in the previous case we saw that the center of buoyancy also remained constant. Okay, the location was, let me go back. Since the body was completely submerged, the location of center of buoyancy was fixed. Okay, because the amount of fluid that was displaced by the body remained constant, no matter how you tilted or shifted the body. But in the case of floating bodies, the amount of fluid that is being displaced by the body changes when you change the configuration of the body. Okay, so in this particular case, the configuration of the body that is being submerged in the water is of this shape rather than this one. Okay, and we saw that the net force that acts on the body, on this submerged body, also depends on the configuration, right? So since the more amount of fluid is being displaced in this direction, or in this part of the or in this half of the body, I must say, displaces more fluid, so the center of buoyancy tends to shift accordingly to balance this particular shift or resist this particular displacement. Okay, so you'll see that initially if the center of buoyancy was somewhere here, let me just draw it. If this is G and this is B, then you'll see that the center of buoyancy now shifts to a new location, say B dash. Okay, here. And to find and now this if we just take the line of action of this particular buoyant force that acts to B and extend it to the central axis of this body, you will see that these two lines meet at a particular location known as, let me name it as M, which is known as the metacenter. Okay, and this distance between M and G is known as the metacentric height. Okay, and you will see that it is the metacentric height that acts as the governing parameter of the stability of these floating bodies. Okay, so so there was a detailed derivation considered by Professor Chakraborty, where he again considered elemental area, found out the buoyant force that acts on a particular area, and carry forward the expression, carry forward the derivation. So it's a good exercise if you just, again, after the class, you go back and look into the derivation. You'll get a lot of idea and perspective. But to save time, I will not go to the derivations. I will just give you a final expression for the metacentric height. So it is given by, if Gm, that is distance between the center of gravity and the point of intersection of the buoyant force and the central axis of the body. So metacentric height is given by Gm, that is this particular distance, which is equal to Cb into M, or where Cb is the, I I think I misplaced the location of the center of buoyancy. So this would be G and this would be B. Okay. CB times M minus CB into G, where CBM, there is the distance between the center of buoyancy and the metacenter is given by IYY times V, where the IYY is basically the moment of inertia of the body with respect to the y-axis, and minus CB into G. Okay, because this thing is something that you have to find out. I'm sorry, this is something that changes with the volume of the body that is being displaced. That's why you need to find out. This is something that you need to evaluate. But these things, CB into G remains constant, because once you know the portion of the body that is being submerged in the body, the distance between the center of buoyancy and the center of gravity is easy to be found out. So this is something that can be calculated, but this is something that you need to evaluate. Okay, depending on the volume of the body that is being displaced by the fluid. Okay, and again, this expression also is quite limited to certain scenarios where theta has to be small and Z is the axis of symmetry of the body. So this is valid for symmetric bodies. Okay, so to conclude this stability part, for floating bodies M should be always be above G, so this will result in a stable equilibrium, and if M or the metacenter is below G, then it will result in a unstable equilibrium. Okay, so so again, these are discussions. Then I think we can skip for now. So for the final part of our discussion, I will just briefly go through this fluid and rigid body motion. So this part again, I think we do not have extensive questions regarding to this topic, at least in my question that I have today. But still, since it was discussed, I will just go through it once. So if you have any doubt, you can ask. Okay, so like even before starting this what to say, fluid static, or I must say right at the beginning of fluid statics part, we were discussing about fluid and rigid body motion, right? Like these equations, that is the Euler's equation, or not Euler's equation of fluid statics. There is equations such as dou P by dou x plus rho bx equal to rho ax. So so there was a discussion that we had in the previous problem solving sessions, that if the fluid body is in motion, then why we are considering it to be a part of fluid statics, or why we are considering this kind of scenarios under the purview of fluid statics. Okay, so Prof. Chakraborty very beautifully explains why. He says that since the body or the fluid element is not undergoing any kind of deformation, or basically if these fluid bodies are exempted from any kind of shear stresses, then the surface forces that acts on these particular fluid elements are same in the case of fluid being stationary or fluid moving in a way which prevents any kind of shear forces, or basically if it's devoid of any relative velocity changes between the fluid layers. Okay, since the surface forces remain same in both the scenarios, that's why we can consider this fluid under rigid body motion under the purview of fluid statics. Okay, so basically, or ironically, as Professor Chakraborty explains, this is not fluid body it is not fluid body at rest, but rather it is the case where the stresses that acts in the case of fluid under this special kind of motion are same as the fluid if it were at rest. Okay, so that's why we can consider it under the purview of fluid statics. So let us quickly take this example. For example, if you consider a particular volume of fluid inside a container which is moving at an acceleration of ax, okay, again a constant acceleration. So if it moves with an acceleration x, the free surface of the body of this fluid again changes accordingly to take into account the changes because of this acceleration. Okay, so Prof. Chakraborty mentions that this is again a very idealized case. He mentions that he says that the approximation that we have to take is that there are no shear forces x on the fluid element, which is actually not true, because if if this is a geometry that we take into consideration, there will always be some always be some shear stresses that will act on the fluid. But again, he mentions that since we get a lot of ideas, when a lot of perspectives, or when we disregard this stress analysis, shear analysis, so this simple analysis can also give a lot of idea of what's happening in the real life, right? So just to simplify our calculations, we take these idealized cases. Okay, so that's the explanation that was discussed by Prof. Chakraborty. So let us go through it quickly. Okay, so he mentions that the governing parameter to locate the free surfaces is given by dp equal to 0, because the free surface of the fluid will be in contact with atmosphere, so the atmospheric pressure will remain constant throughout its area, so the pressure at the free surface would remain constant. So that's why dp at the free surface would be equal to 0. Okay, and since we are considering a 2D scenario where of course it's continuous, the surface would be of a 2D shape, then the pressure would be a function of x and y. Okay, then pressure, this p, like if we consider, since it's function of x and y, then dp, that is a complete derivative of pressure, will be given by dou p by dou x dx plus dou p by dou y into dy. Okay, so this thing, like, I know most of you may already know if you have taken some PDE courses or even differential equation courses, but if you do not know, you can just take it for now, like this will, you can understand it for now, like a complete differential of a function. Say if f is a function of x and y, then df would be given by dou f by dou x dx plus dou f by dou y dy. Okay, it's something that you study when we get introduced to partial differential equations, and this will again be quite handy when we discuss about stream functions. Okay, so we can take it as a, I would say, note for now, but you can also look into it if you have any time. Okay, so so we have the dp, that is the complete derivative of p as dou p by dou x plus dou p by dou y into dy. Then if we take if we consider equations of fluid statics, we'll have that dou p by dou x in the along the x direction, we'll have dou p by dou x is equal to rho x, because there is no body force along the x direction. Okay, sorry, so dou p by dou x will be equal to rho x. Let us name it, it's equation 1. Then along the y direction, along this direction, y direction, we will have dou p by dou y plus rho by is equal to rho ay, and since there is no acceleration along the y direction, so this is equal to 0, and by would be equal to minus g, that is the direction of the acceleration of gravity. So dou p by dou y will be equal to rho g. This is again the hydrostatic law. Okay, so if we substitute the value of dou p by dou x and dou p by dou y in this equation, you will get that rho ax dx, sorry, minus rho x dx minus rho g dy equal to 0. Then we can say that dou y by dou x is equal to minus ax by g, which is basically the slope of this particular free surface. Okay, free surface. So we can write as tan theta is equal to ax by g, where if we look into this expression, then say if this is your displacement, say if this is total displacement theta, then this would be, say, delta h. Okay, delta h by b, delta h by b would be equal to tan theta, or that would be equal to ax into g. Okay, so delta x, sorry, delta h, okay, sorry, so consider b by 2. Okay, okay. So just give me 1 second. I'm sorry, I got confused in this part. So let us not look into that, look like that. So let us say that this displacement, say if this is equal to b, then or say L, let us say, then delta H by, sorry, L would be tan theta or ax by g, or delta H would be ax by g into L. Okay. Then we can, once we know this parameter delta H, you will get to know whether the fluid inside this particular container will spill out or not. Okay, so again, this kind of analysis will help you to know that what will be the minimum value of acceleration that would maximum value of acceleration that we can reach in this kind of scenarios to prevent the fluid inside the container to spill out. Okay, so that's why this kind of analysis are done. So keeping our discussion up to here, let us look into some questions. Okay, so are there any doubts like till now? Okay, then okay, thanks Pradeep. Then let us look into some questions. Oh, I'm sorry. Yeah. So let us look into the first question. So again, this is a correct incorrect type of question. So which of the following statements is or are incorrect? Okay. The hydrostatic force on a submerged horizontal flat plate at rest is same as that of a plate submerged horizontal flat plate rotating uniformly around the vertical axis passing through its centroid. Okay, so it's a quite extensive sentence, so let me try to simplify it for you. So they're saying that if a flat plate is placed like this, like submerged in a fluid, okay, that's the first case. And the second case is like if you're rotating this flat plate with respect to this vertical axis, that is case 2. So they're saying that whether the hydrostatic force that acts in these two cases, in the first statement they say that is same. The first statement says that the hydrostatic force that acts in these two scenarios are the same. Okay. The second statement says that the hydrostatic force on this submerged horizontal flat plate at rest is pi times greater. Like this force is pi times greater than this force that acts on this particular case. The third statement says that this hydrostatic force on this plate is pi times less than this force that acts on this particular case, rotating case, or third is all of the above. So which of the following statements is or are correct? So a hint would be to look into the expression for the hydrostatic force on submerged bodies. So you can look into it, like see on which parameters does that force depend upon. So does that force take into account the rotationality of the submerged bodies? So you can look into that and then let me know which is the correct answer. Okay, it's an actually nice question to look into the very concepts of fundamental concepts that were discussed today. So you can tell me which is correct. A. Oh, I'm sorry. Okay, A, you are saying correct. So basically you are saying B, C and D. Okay, D is not an option, so you are saying B and C are incorrect, right? Is it? Or you are saying A is incorrect? Yes, okay, so Pradeep mentions that B and C are incorrect. Okay, so what about others? Like, what do you suggest? One more answer, then I think we can then look into the next question. Someone? No, no issues. Like, you can just give a try. I also written the expression F is rho g A into hc. So does this expression take into account the rotationality of the submerged body? Okay. So the thing is, no. As Pradeep mentioned, correctly mentioned, the correct answer is B and C. That is, B and C are incorrect. So basically, the answer would be that the hydrostatic force that acts on this first case, that is a flat plate submerged in the fluid, and the second case, the flat plate submerged in a rotational submerged into the same depth, which is rotating about this vertical axis. So this will remain same since the depth at which these bodies are being placed remains constant even after the rotation of the second case. That's why the hydrostatic force that would act on this particular scenario would remain same. Okay, since this and this remain constant, area does not change when the body rotates, and the depth at which it was being placed also does not change, so it will remain constant. Okay, so this is the right statement, but the question is which are incorrect, so B and C would be incorrect. Okay, next question is again a statement type question, statement assertion type question. Dams are built thicker at the bottom part. That's the statement. And the second statement is bottom part of the dams are subjected to largest forces as the pressure distribution or the force increases with depth. So which among the following options are correct? Both statements are individually true, and statement 2 is the correct explanation of statement 1. Both statements are individually true, but statement 2 is not the correct explanation of statement 1. Statement 1 is true, statement 2 is false, statement 1 is false, statement 2 is true. So which is the correct answer? It's something that we discussed right at the start of today's discussion, the pressure distribution. Okay, Pradeep says A. So others, can you give a try? Again, a conceptual question, nothing to calculate or find out. Look, recall the pressure distribution that I discussed at the start of the class, like mentioning that pressure distribution, how it increases as we go in the downward direction because of the hydrostatic law. Okay, so one more I would actually like if someone else also. Okay, Sanu says A. So yes, so this is correct. Yes, since we saw that the pressure distribution in the case of hydrostatics increases linearly with depth, right? We saw something like the pressure distribution increases something like this, right? So since the bottom part of them are dams are like experiencing the highest amount of pressure forces, that's why it is just wise to build the bottom parts of the dams to be thicker than the upper parts, right? Then you may ask, then why not just build something like that, like if this is the minimum depth or width required to handle this amount of pressure, then just to make it look more aesthetically pleasing, make something like this, like same area. But again, we are engineers, right? In the perspective, from the perspective of engineers, we need to look something that is more economically feasible. So if there is a geometry or structure that is able to handle pressure with this particular width rather than having a greater width, then let us put it with the minimum amount of or not minimum amount, I will say minimum amount plus the considered factor of safety for a particular structure. Let us use that amount of materials rather than using that the amount of material that is not required. Okay, we have to look into the cost part as well. So that's why this kind of design is used in the case of dams. Okay, both considering the pressure distribution as well as the economic perspective. Okay, so let us look in the next question. So next question, I think, okay. Next question is, on a plane surface, sorry, on a plane surface, the hydrostatic forces form a system of parallel forces, and we often need to determine the magnitude of the force and its point of application, which is called the center of gravity. So is it true or false? I think it's very simple. The hydrostatic forces, do they act through the center of gravity, or there's another name for a particular point? So if yes, then the statement would be false, right? Or if no, then it's true. So which is it? Someone can give it a try. Question number 3, quite simple. Yes, exactly. So it is known as center of pressure. So this is false. So yeah. Okay, this is repetition of the question. So let us not consider this one. For a floating body, the buoyant force acts at the A, centroid of the floating body, B, center of gravity of the floating body, centroid of the fluid vertically below the body, or centroid of the displaced fluid. So which is the correct option? A, B, C and D. D. Okay, so this is correct. So this is something that we dealt just previously. Last part, that was we were discussing about the metacenter and the metacentric height. So we saw that the stability of the metacenter and the metacentric stability of the floating body depend on the metacenter, and this metacenter and metacentric height is a function of the displaced volume of the fluid. Something we something so like gm is equal to Iyy v minus cbg, right? So this v is actually the volume of the displaced fluid. Okay, volume of the displaced fluid, sorry. And this expression or this derivations in one way or another takes into account the shift of the center of buoyancy of the submerged body, or the partially submerged body in the in this analysis. Okay, so next question is question number 5, I guess. For a completely submerged body with a center of gravity G and the center of buoyancy B, the condition of stable equilibrium will be that G needs to be located below B. So is it true or false? Completely submerged, G needs to be below B. So is it true or false? So Pradeep says it's true. So let us wait for other responses as well. So is it true or false? Stability of completely submerged bodies. So we saw that these are completely governed by the location of the center of gravity and the center of buoyancy, and the governing criteria was that that the center of gravity has to be below the center of buoyancy. Okay, then only they form a restoring couple. So this is true. Okay, so next question. So this is a bit extensive question, so I would require you to thank Sanu. Sanu also said true, so it's correct. So question number 6 is a bit involved question, so I will require you to bring out your pen and paper and calculators to do the evaluation. Okay, so the geometry is given here. it's something like the fluids. I think I can zoom in a bit more. Yeah. So this is the free surface of the fluid. Okay. And the curved surface is of this shape. Okay. This shape, and all the geometrical parameters are given to you. The question is, a sector gate is provided on a water spillway as shown in the figure. Assuming G is equal to 10, okay. Say, I'll always mention that, yes, somebody mentioned, okay. So I always mention that unless and until mentioned then G is something, you should always take G as 9.81 or 9.8, whatever you feel suitable, preferably 9.81. But since in this question they exclusively mentioned G to be 10, so you need to take the acceleration, you need to give it T as 10 meter per second square. And density of the water, that's constant, so it is not constant, I would say in ideal conditions is 1000 kg per meter cube. So density of water is 1000 kg per meter cube. Find the resultant force per meter length of the gate. So consider the width of the gate to be of 1 meter. So we need to find the resultant force that acts on this curved surface. Okay. So again, concept is you need to find FH. Since the geometrical parameters are given, you know the geometry. So you need to find FH and FV, then find the net resultant force. Okay. So my hint to you would be that this is not a semicircle, as you can see. You can see the angle that is being. So you cannot consider this to be a semicircle. Actually, this entire part can be considered to be a sector of a circle, basically a portion of a circle, rather than a semicircle. Okay, you cannot consider this part to be a semicircle. They have not mentioned anywhere this is semicircle. Okay, so this portion can be considered. Actually, these are the lines that are drawn to define the geometry. So the actual geometry is only this part, this curved part. But the other lines that are shown here, they help you to understand the geometrical features. So given this condition that this distance from here to this part is 5 meters, so you can consider this to be a particular sector of a circle rather than a semicircle. Okay. So with that hint, you can try it out. So the first task would be to find the horizontal force or a vertical force, whatever you may want. The horizontal force is quite simple. You need to find the force that acts on its projected surface. So projected surface is again a rectangle of length. You need to find this particular length. So this length you need to find. It's again easy. 5. It will be 5 cos 30. 5 cos 30 plus 5 cos 30. So 2 into 5 cos 30 times 1. So that will be the projected area. And then times rho GH. Okay. HC again would be the center of gravity, would be again 5 cos 30. Okay. I'm giving you hints. So with like this you can find the horizontal force. Then vertical force would be to find the volume of fluid that would have been held by this portion of the geometry. Okay, that's a bit more challenging. So that's where you need to find the area of sector, of area of this particular sector. Oh, I must and minus the area of this triangle. Okay. So you can try that. I will give you say 5 minutes, or let me. Okay, I will wait. Okay, I will wait till 7:42, and then let's see whether you can try it out or not. Okay. I think the question is clear. I have tried to explain as simple as possible, but I think I gave enough hints as well to approach the question. But again, if you have any doubt, you can just put in the chat box. It's fine. So 1 more minute. Again, see, there is no actually say case like if you're not able to solve it in 5 minutes. It's an extensive question, difficult to understand initially. I also made mistakes when I tried to solve it. It's fine, but since we have limited time in the class, so I'm just going a bit fast, giving a limited time for some particular questions, but it's completely fine. More important thing is to understand the concepts and to understand like what particular formula we need to choose, what is the geometry that is under consideration. So in this case, the typical mistakes that students can do, yeah, so that's what I was mentioning. So typical mistake that the students can do is that consider this geometry as semicircle. Okay, so it's not the case. 179.61 kilonewton, Sanu says. So okay, so let us okay, that's Akash. Oh, sorry, not Sanu. Akash says. I'm sorry, I just confused. Okay, so since I will explain again. So the thing is, area would be actually the area of this particular sector. Okay, this is not a semicircle. So if it would have been a semicircle, they would have mentioned this particular diameter radius, then it was fine. But the shape itself does not seem like a semicircle. So actually, it should be considered as a sector. Sector mean a particular area of the circle. Okay, so a particular portion of the circle. So to find this area, you need to find the volume of fluid contained in this curved surface, right? To find that, you need to find the area of this particular region, and times the length would give you the volume. So the area would be the area of this sector, right, minus the area of this triangle. Okay, so if you don't mind, like, I can just go to the answer once. I know everybody will have tired a lot, but it's fine. Just for saving time, I'm going to the answer. Then there's one more question, extensive question, so we can give some time to that as well. Okay. So this is the geometry as I was discussing. So this is the distance from A to O that was mentioned in the diagram. I just labeled it as A, B, and O. So this, the area of the, to find the area of triangle, you need to find half into base into height, right? So if we consider a triangle of this shape to make it a right triangle, then right angle triangle, then height would be 5 cos 30 and base would be 2 times 5 sin 30, right? So the horizontal force or Fx would be rho g h bar times A. Rho is 1000, g is 10, h is 2.5 because 5 sin 30 would be half, so 5 times half would be 2.5 times the area would be again this 2.5 plus 2.5 is 5 into 1, right? So projected area is the rectangle of area 5 meters square. So the net horizontal force is 1000 into 10 into 2.5 into 5 into 1, it is 125. Okay, so to find the weight or the vertical component of force, as I mentioned, you need to find the area of the sector minus area of triangle, and basically would be into 1 because the width of the this geometry is 1, right, as mentioned in the question. So area of the sector would be theta divided by 60 into pi r square, where theta is the enclosed angle of this particular sector, which would be 60 degree in this particular case. 30 plus 30 is 60 degree, times pi r square. R is 5 as mentioned here. Yes, and area of triangle will be half times base into height. Half times base is 2.5 is 2.5, is 5 times 5 cos 30, right? 5 cos 30, 5 into root 3 by 2. Once you do the calculation, you will get 60 divided by 360 into pi into 5 square minus half into 5 into 5 cos 30. So it will be 13.09 minus 10.825. That will give you 2.265 meter cube. Okay. Then Fy, that is the vertical component of force, will be 1000 into rho g into V. So 1000 times 10, that is G, into 2.265, that is a volume, that is 22.65 kilonewton. And then the resultant force would be 125 square plus 22.65 square, that will give you 127.03 kilonewton. So that will be the correct answer. So I hope I know everybody would have tried accordingly, correct, they are going the right direction. So I just gave you some hints. So if you have any doubt, you can ask. So I hope it is clear. If you have any doubt in the solution methodology, you can ask. It's fine. I hope Akash, you can clarify the mistake that you would have done in the steps. I think it would just be a calculation mistake. Yeah. Okay, it's fine. Thank you then. So let us look in the next question. Sorry, let's close this. Yeah. So correct answer is none of this. Okay. So next question is a triangular gate with a base of 2 meter and height. Okay, let us underline these terms. A triangular gate with a base width of 2 meter and a height of 1.5 meter lies in a vertical plane. Okay, so triangle 2 meter, 1.5 meter. The top vertex of the gate is 1.5 meter below the surface of the tank. So this is at a depth of 1.5 meter, which contains a liquid of specific gravity 0.8. So density of the liquid would be
Sg times raw water, that is 0.8 times 1000, that will be 800 kg per meter cube. Okay. Considering density of water and extraction of gravity is 1000 kg per meter cube and 9.81. Here you have to take 9.81. Okay. What is the magnitude of hydrostatic force included and exerted by the liquid on the gate? Okay. So it's quite simple. So not that you just need to find a hydrostatic force. Okay. F, that is rho g a into h bar. So h bar would be the depth or the center of gravity of this particular triangle. Okay. So again, it would be a good exercise for you to find out what is the center of gravity of a triangle, or in this case a right angle triangle. So what's the expression for the center of gravity of a right angle triangle? Because once you know this length or this length, like either of the length, like center of gravity of the right angle triangle from its base or from its vertex, anything, you can usually find h bar, and all these other parameters are given to you, right? So just do that and let me know. So I will give you say 5 minutes again. I think that should be enough. Try it out. It's quite simple, not that complicated, and then let me know which is the correct answer. 29.43. So Pradeep says it's 29.43. So let us just wait for one more try. Let me wait till 7:54, then let us see. Okay. Thanks Pradeep for the answer. Let us see whether others answer also match with you, and then we can just look into the solution. So as I said, like these kind of questions are actually a very good exercise to revisit your geometry notes, like finding the center of particular shapes, and then understanding how you can apply that to find the center of gravity of these particular shapes. So it's a good exercise. So, yeah. So as a precautionary measure for your exams, I must say, it would be just a good practice to look into the basic formulas for the center of gravity of some generic shapes such as triangles, semicircles, right? Or formula for some particular shapes, cylinders, cones, like that. Then it will become quite handy for you. Just saying, like, just another formulas. So exam you may not get the opportunity to look and find it, right? So you can just recall it once you,
because once you know that, then these questions become quite handy, right? Quite simple to solve. Okay, one more minute, then we'll look into the answer for this question, and then I think there's one more statement type conceptual question, then we can just end today's discussions. Okay, so it's 7:54 already. So let me say, Pradeep, the answer is correct. It is 29.43, but let us look into. So correct answer would be option C. But nevertheless, let us look into it how we got up to that. Okay. So this is a geometry in our hand. As I already drew already in the question part. So the depth of the center of gravity of this particular geometry would be 1.5 plus 1.5 times 2 by 3. Okay, so again, someone asks what is 2 by, why we are doing 2 by 3. Okay, so for a center of a right triangle, okay, that is it's where the height of this triangle is perpendicular to its base. So in these cases, in this case only, the centroid of the circle is at a distance of h by 3. So if the height of that particular right triangle is h, then the centroid of the triangle is at a distance of h by 3 from its base. Okay, or in general formula for finding the centroid of a triangle, say if the center of triangle is at a location of x bar and y bar, the center of the triangle is given by x1 plus x2 plus x3 by 3, comma y1 plus y2 plus y3 by 3, where x1, y1, x2, y2 and x3 by 3 are the coordinates of the vertices of the triangle. Okay, so we just needed this formula in our hand to find this. So once you know that, so if this is h by 3, then this distance is 2 by 3, right? 2 by 3 of h, right? And we need this distance. Okay, so we can write 1.5 plus 1.5 times 2 by 3. So we'll get h bar as 2.5. Okay, or if again it's quite simple, but like if you don't want to do that, like you know h by 3, then you can just do something like 1.5 plus 1.5 is 3 minus 1.5, something like that. Okay, or 3 minus 0.5, that is 1.5 by 3, this is 0.5. 3 minus 0.5 will again give you 2.5. You can do like that as well. It's just the way you do it, it's fine. Then fh will be rho g into h bar into a. Rho is 800, g is 9.81, h bar is 2.5, and a is half into base into height, the area of a triangle. So once you calculate it, you will get fh as 29.43 kilonewton. Okay, so let us, so I think that was the last question. Yeah, I think that's the last question. So yeah, that's all for today from my end. Then let's meet in. Thank you again for having such an interactive session and taking extensive part in the discussions. Thank you for that. So that's all from my end, and thank you. Let's all meet in the next question 9 of week 4 assignment. Okay, so a open rectangular tank of is 3 meter high in water of, okay, what should we take the height of the tank? Open rectangular tank, I don't know, I haven't checked the question. So height of tank, see, this depends on the question. I don't know what the question is. If it's asking something like finding the net force that acts on the particular, say, shape, then you need to take the height h. Always take the h as the height up to which the water is contained. Okay, so that's the hint. Okay, I hope that's fine, because I don't know the question. I haven't seen the question, so I don't know, because I'm just a TA of this course rather than the instructor, so I haven't seen the question, but the hint would be that, not hint, I think what I can say from mine is that take the height h. If it is regarding finding the hydrostatic forces, then take height h as the height up to which the water is contained. Okay. So as it seems geometrically it should be 4 meter, but if 3 meter is coming into the picture, it seems like tank of 5 meter is 3 meter high. I don't know. I'm sorry. I hope you don't mind. Then okay then. So let's meet. Yeah, thanks, Pradeep. Sorry, I haven't seen the question, so sorry for that. So let's meet in next week. Okay. Thank you, everyone.